So, welcome to week 7 of the problem solving session. And today we'll be solving some more problems on root locus. And we will see how can we design root locus when we have positive feedback in place of negative feedback, or when k varies from minus infinity to 0, that is when k is negative. So we will see problems on these topics. Okay, so let's get started. Okay, for the first problem, we have the root locus of some unity feedback system which is like this. So this is the j omega axis, this is the real axis, and we have the poles at -1 and -2 of the open loop system. This denotes k equals to 0 point. So the root locus is like this. So in this problem, what will be the closed loop transfer function? Find out the closed loop transfer function. Okay, so for the given root locus, you have to find out the closed loop transfer function of the system where we have open loop poles at -1 and -2, and the root locus is marked as this red lines. Okay, so starting from poles, these poles, and it is tending to plus infinity and minus infinity. Okay, I think there's network issue from my side. Just a second, I am reconnecting. So my screen is visible now. I hope it is visible. Okay, what will be the closed loop transfer function of this system? In this problem, if you observe it carefully, you may observe that it doesn't satisfy the odd number of open loop poles and zeros criteria to the right, because if you pick this point which is beyond -1, you will see that on the right there are no open loop poles and zeros on the real axis, but still we have the root locus. Similarly, if you look at the point between -1 and -2, you observe that at this point to the right we have one open loop pole which should satisfy the odd number of open loop and zeros criteria, but still we have no root locus on this real axis. Then what does it mean? It means that we don't have a negative feedback system. Even though k is we are increasing k, so k is positive, but the feedback is not negative because we have complementary root locus in this case. So what should be the closed loop transform function in this case? So the answer is, instead of negative feedback we have positive feedback closed loop system. Okay, so for this case we can easily calculate the open loop transfer function first, which is g of h will be nothing but k divided by s plus 1 s plus 2, because we have open loop poles at -1 and -2, so the open loop transfer function will be nothing but k divided by s plus 1 into s plus 2. And then we have to find the closed loop transfer function. So what will be the closed loop transfer function in case of positive feedback? So we know it is, instead of 1 g divided by 1 plus gh, it is 1 minus gh, and h is 1 because we have unity feedback, right? Now what will be the closed loop transfer function? Can you calculate now what it should be? So it will be right, which will give you k divided by s plus 1 s plus 2 minus k. So this will be the closed loop transfer function of this root locus, right? So in problems, when you encounter such type of root locus, please check if it satisfies the zeros and poles criteria, that is even number or odd number. So by checking that, you first um, ensure whether it is a positive feedback or a negative feedback system, and then you finally calculate the closed loop transfer function, right? So based on this concept there will be questions. Okay, so similar to that we have another question where there is open loop transfer function of a negative feedback closed system. So here the feedback is given which is negative, that is good. and it is given as k divided by s cube plus 2s square plus 5s. But now the catch is here, k is not positive but it is non-positive, so k is less than equal to 0. Okay, consider the locus of the corresponding closed loop poles and identify the region of the real axis that lies on the root locus. Which region of the real axis will lie on the root locus? Okay, please try it. Okay, so first let's calculate the open loop poles for this transfer function, k divided by s cube plus 2s square plus 5s. So we have poles at s equals to 0 and another poles will be located at, so we need to solve this quadratic equation. What will be other poles for this system? If you solve the
minus 1 plus 2j minus 1 minus 2j.
yes, correct. So the poles are s equals to 0, minus 1 plus 2j, and minus 1 minus 2j. Okay,
Minus 1 minus 2j.
yes,
Yes.
thank you. Now if we plot it in the s plane, this sigma, this is j omega, where will be the poles lying? It will be at 0, minus 1 plus 2j, and minus 1 minus 2j. So these will be the open loop poles. Now since k is negative in this case, k is not positive, so where will the root locus lie on the real axis? So it is a kind of complementary root locus. So in that case, the part that will lie on the real axis, it will be such that on the right of that part, the number of open loop poles and zeros should be even or odd?
Even.
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 Yes, now since we have marked the open loop poles, now can you identify the part of the real axis that will be lying on the root locus? First, let's
0
check.
to infinity.
Yes, first let's check this part. So this part, what do you think? So this part we have, to the right of it there are no open loop poles and zeros. Okay, and what about this one, this part? We see that we have odd number
1.
of open loop poles and zeros, right? So this part is not going to lie on the root locus because we have encountered odd number of poles to the right of it. So the part that will be lying on the root locus will be this part, okay, which is 0 to infinity.
Ma'am, how on left of line it's odd number?
Sorry, can you repeat please?
How in the left of line it's odd number also?
Okay, we have to see the open loop poles and zeros lying on the real axis, okay. So if we see this part, okay, if with this part, and if we see the right of it, how many open loop poles and zeros are lying on the real axis? Only one, that is the 0, okay.
Yes, ma'am.
You can pick any point like this point, and the right of it has only one pole which is lying on the real axis. So we have encountered odd number of poles. Since we have no zero, so we are not talking about zero, so we have encountered odd number of poles. So this doesn't satisfy the ultimately angle criteria in the case of when k is negative, right? So it is a kind of complementary root locus. That's why we are checking the even number of poles and zeros. Since number of poles are odd in this case, so this part is not going to lying on the root locus. But if we check this point, there are, to the right of it, there are no open loop poles and zeros, so that is also not odd. So we say that we have root locus lying on the right of it, okay.
Yes.
Okay, so for the previous problem, which of the following statements is true? So first statement is, let me write the open loop transfer function, which was k divided by s square plus 2s plus 5, where k is less than or equal to 0. So for this problem, you have to identify the correct statements. The first statement is, it would have three asymptotes. The root locus would have three asymptotes, or it would have the positive real axis as the only asymptote, or it would have the negative real axis as the only asymptote, and the last one is, it would have both the positive real axis and the negative real axis as the asymptotes. So how many open loop poles we have in this case? Since we know that
3 open.
number of asymptotes is nothing but n minus m, right? Number of open loop poles minus number of open loop zeros. Since we have no open loop zeros and we have three open loop poles, so the total number of asymptotes will be 3.
What is M, ma'am?
Sorry,
M.
m is the number of open loop zeros, n is number of open loop sorry, open loop poles, and m is the number of open loop zeros. Because the correct answer is, in this case, that it has three asymptotes, which is very clear. Okay.
Ma'am, how is the number of open loop zeros? M.
From here we can identify, this is the open loop transfer function g of s, and here we have three poles, because one pole is s equals to 0, and another two poles are minus 1 plus 2j and minus 1 minus 2j, that we have already calculated in the previous question. So total we have 3 open loop poles. And zeros, we have no zeros because we have nothing in the numerator. Okay, so there are no zeros in this transfer function.
If there is S function in numerator, then it's number of open loop zeros.
If there is something like x plus 2, then we would have s equals to minus 2 as the 0, so we will be having 1 0. Okay, so m will be 1 in that case, and then we have 2 asymptotes. But
Okay.
since we have no
Yes.
numerator, so m is 0. We have no open loop zeros. Okay. Again, for this problem, we have to comment about the break-in or breakaway point. Check whether we have any breakaway or break-in point in the root locus. And how to check the break-in or breakaway point? How can we check? So we need to
First we write
the yes,
characteristic equation.
yes. First we write the characteristic equation, which is nothing but, if we write it as k a of s by b of s, where a of s is 1 and b of s is s into s square plus 2s plus 5, then characteristic equation is nothing but 1 plus g h equals to 0. H is 1, so 1 plus g equals to 0, or 1 plus k as by bs equals to 0. Okay, and then since we have repeated poles, we would be having repeated poles at the break-in or breakaway point, so this boils down to finally finding out b dash s into as minus, that is derivative we have to put to 0, as a dash into bs equals to 0, where b dash and a dash are the derivative of b and a with respect to s. So what will this equation give us? So a dash s will be 0 because it is 1, which is constant, so its derivative will be 0. What will be b
3,
dash s?
3s square plus 2 equal to 0.
Yes, b dash s will be s square plus 2s plus 5 and plus 2s plus 2 into s. So this will be s square, sorry, it will be 3s square and 4s plus 5. This will be b dash s, and then calculate this b dash a minus a dash b equals to 0. What you will get? If we calculate it, we will have 3s square plus 4s plus 5, and a is 1, so just multiply 1, and this a
No,
dash is
5
0, which is
constant.
0. Okay, what will be s then? As we have already calculated, s will be minus 1 plus minus 2j. Okay, now we have to put this s equals to minus 1 plus 2j and s equals to minus 1 minus 2j to our case, which is k equals to minus ps by as, right? We have to put these 2s in this equation, and we have to calculate for k. What you will get then? We have bs as s, it was
SQL plus 2s plus 5.
square plus 2s plus 5. No, have I calculated this correctly? I think this s will be different. It will be different, I think. Please calculate this. It will be minus 4 square minus 4 by 12. Okay, so we'll be getting some complex roots, right?
It is correct, ma'am.
Yes,
Correct, it is correct.
this one we will be getting.
Yes.
I don't think so, because we have 12 here. So this will be 6.
No, 5 won't come. No. B dash of s.
Some roots will we get which will be complex. So this complex roots, it will mean that we don't have any breakaway or break-in point, right? When you calculate it and you put k, you will not get k as less than 0, right? So what does it mean? It means that it doesn't satisfy our criteria, because in our transfer function k should be negative. So it boils down to the fact that we don't have any breakaway or break-in point. Okay, and why I'm saying so? Because see, the break-in or breakaway point occurs at where it occurs on the real axis, right? If we have sigma and j omega, the break-in and breakaway point occurs, for example, if we have a breakaway point, it will occur between the two poles, so our root locus will go out. Or if we have zeros, then the root locus will come in. So this denotes the break-in point, and this denotes the breakaway point, and it occurs on the real axis, right? So our s will have only real part, but when we are calculating it, what s we are getting? We will getting some complex number because this term is negative, right? So s will be, we are getting complex roots. Since s is not real and the break in and break away point occurs only on the real axis, what we can say? We can say that we don't have any break in or break away point. Okay, so the moment you get complex roots by solving this equation, you can conclude that we don't have any break in or break away point. Is it clear? Any confusion to anyone? Okay. Okay, so for the previous problem, which has the open loop transfer function as, I'm again writing so that you can easily do the calculations. It was s square plus 2s plus 5. You have to calculate the angle of departure of the root locus from the open loop pole at -1 plus 2j. Okay, we had poles at these three locations. It was -1 plus 2j, and this point was -1 minus 2j. This point was 0. Okay, and from this pole location you have to calculate the angle of departure, because we know when we have complex conjugate poles and the root locus starts from the open loop poles, so we don't know from which angle our root locus will depart from this pole location or this pole location. So for that we calculate the angle of departure. By calculating the angle of departure, we would know with which angle the root locus will depart from here or from here. So in this case we have to calculate for this pole -1 plus 2j. Please try it. And keep in mind that we have k as non-positive. We have negative feedback, but we have k as negative. So what we have to calculate first? We have to calculate all the angles that this pole makes with rest of the open loop poles and zeros, right? First we have to calculate that angle. So let's call it angle A, which is this angle. So first, what angle this pole is making with the other open loop pole? So let's take the first open loop pole as 0. What will be this angle A? So it will be what? It will be 90 plus this angle. And what will be this angle? It will be what? Tan inverse of
1/2.
yes, tan inverse of 1 by 2. So 90 degrees plus tan inverse of 1 by 2. How much it will be? It will be 90 degree tan inverse of 1 by 2. It is since we are calculating in degrees, so it will be
116.56.
okay. So you are added it as well. 116.56. Okay. And where is the other open loop pole? This conjugate one. What angle this pole will be making with this one?
90 degree.
90 degree. So this angle B will be 90 degrees. Now what will be the angle of departure? Now since we have negative feedback but K is non-positive, that is negative from minus infinity to 0, the formula here, instead of 180 degree it will be 0 degree, right? Because the angle criteria will change in this case, and it will be minus of angle made by sum of the angles made by open loop poles and plus sum of the angles made by open loop zeros. So this goes to 0 because we have no open loop zeros, and the angles made by the open loop poles, it is 116.56 plus 90 degree. What it will be? Minus of how much? 56
206.56.
206.56 degrees. Yes, but we don't have any option in negative. What will be the answer then? So the angle is like
360 minus
minus of
206.56.
206.56. So if we subtract it from 360, how much we will get?
153.4.
Yes, correct. So the answer is 153.4 degree. Okay, in the counterclockwise direction. So the correct option is this. This is clear to everyone? Okay then. Okay, what will be the stability condition? For what range of K the closed loop system of the same problem that we are solving is stable? That's very easy to follow. Let's again draw our poles and zeros. So we have only poles. Okay, my root locus will start from these points, that is the open loop poles, and at this point K will be 0. That is clear? Okay. Now as we are varying K, right, since we have K as negative, and we have already seen where our root locus was lying on the real axis. It was this part. Okay, and we were varying K, and the root locus will be lying on the right half plane, and we are K is varying in the negative side, means minus infinity to 0. Okay, and we are encountering closed loop poles on the RHS. So what do you think? Will there be any point on root locus that will give us a stable closed loop poles?
No, ma'am.
No, because we have already seen that for all k which is less than 0, our closed loop poles, that is the root locus, one of the poles is always lying on the RHS of the S plane. Since any pole on the RHS will not allow the closed loop system to be stable, so the correct answer will be D. There will be no value of k which is less than 0. Of course, we are varying it for negative values. No value of k will be able to give us stable closed loop poles. Okay then. So for the same problem in which we were having negative feedback, now the feedback is positive and everything else is same, means k is still negative, but the feedback is changed to positive. Which option is true? So we had g of s as k by s square plus s cube plus 2s square plus 5s. This was our open loop transfer function and k was less than equal to 0. But now instead of negative feedback we have positive feedback. Now what can we comment on the root locus now? The options are: the locus of closed loop poles would have only one asymptote. All the branches of the locus of closed loop poles would lie in the left half complex plane for a finite range of k. The closed loop system would be stable for all k less than 0. And the last is: the locus of closed loop poles would have only one breakaway point. What do you think? See, the option was is for sure not correct. Why? The number of asymptote will change by changing the feedback, because the number of asymptote depends on the number of open loop poles and zeros, so that is not changing, so number of asymptotes will remain same, that is 3. Okay, so first option is not correct. Second option is saying that all branches of the locus of closed loop poles would lie in the left half complex plane for a finite range of k. That we need to check. So, and that we can check by plotting the root locus. Third one is saying that the closed loop system would be stable for all k less than 0. That we also need to check. And the last one is: the locus of closed loop poles would have only one breakaway point. A breaking point, what do you think? It will change? I don't think it will change, because our b and a remains the same. Okay, so in this case also we'll be getting complex poles at the break-in or breakaway point, so that means there will be no break-in or breakaway point. So the last option is also not correct. Then how to verify the second and third option? Okay, now since we plot this closed loop characteristic equation, and this locus is nothing but the root locus, and in this case we have positive feedback. Okay, so what it will be? It will be 1 minus k of g of s equals to 0. Here k was negative. Here also we have k as negative. Now can we write it as 1 plus k dash gs equals to 0, where k dash is equal to minus k and this is greater than 0? Can we write this thing as this one? Are they equivalent? we have positive feedback, so our characteristic equation changes like this: 1 minus kgs equals to 0, and k was negative, right? So instead of k, we have put k dash and we have changed the sign to plus, and this k dash is nothing but minus of k. Now this is nothing but our characteristic equation, characteristic equation which resembles the one that is with negative feedback. And this k dash is also positive because k is negative but minus k will be positive. So the way we used to draw the root locus for k positive and negative feedback, this also is same like that. Okay, now can you comment? Now let's see how our root locus will vary. Okay, so our open loop poles and zeros are going to be same, that is 0, this and this. Okay, now which part of the real axis will be part of root locus? Now that complementary root locus will convert it to the non-complementary one, the one that we used to draw originally. So which part of real axis will be lying on the root locus? So let's pick this right one. This green part will be part of root locus or not? We have to check, in this case, the odd number of poles and zeros criteria, because this is nothing but k dash positive and negative feedback. Okay, and in that case what it says, that the real part will lie on the root locus if on the right of it we have odd number of poles and zeros, open loop poles and zeros. So this part, is there any odd number of poles and zeros to the right? No.
No.
So this part is not going to lie on the root locus.
Root
What
locus.
about this part?
This will lie on the root
So
locus.
if we take any point here and to the right of it we check, we have one
One pole.
pole on the real axis, so this part is going to lie on the root
Root
locus. Now
locus.
what can we comment? Our root locus will start from this pole. Let me draw it. Our root locus is going to start from these three poles. Okay, because root locus starts from the open loop poles and terminates at zeros or towards the asymptotes in case of no zeros. So it is going to start at k equals to 0. It is going to start from these locations, and as we vary k dash from 0 to infinity, so this is k dash, it will go somewhere. Okay, maybe, and this part is not going to be on the right, it will be on the left, right? Because this part is not going to be on the root locus, so it will go to left. So for some value of k, what do you think? All the poles are going to lie on the LHS or not? For some finite k or k dash, our all the closed loop poles are going to lie on this plane, on this plane only. Are you getting it? So it may go out at some point, it may cross the imaginary axis and go on the RHS, but for some finite value of k, for some k dash between 0 to some value, all the closed loop poles are going to lie on the LHS, because this the branch from this open loop pole is not going to the right, it will go to the left, right? And these two poles are already on the LHS, so it will start from here only. It may cross the imaginary axis and go outside to the LHS, but for some range of k, all our closed loop poles are going to lie on this part of S plane only, because it will start from here, it will start from here, and it will start from here. So for some k, our locus will explicitly lie on the LHS. Okay, now let's see the option. The second option is all the branches of the locus of closed loop poles would lie in the left half of complex plane for a finite range of k. What can we say? Is this a correct option or not?
Yes, correct,
Yes,
correct.
yes. So this one is the correct option. What about the third one? Is it so that our root locus will be lying on the LHS for all k? So how to check that? If there occurs a point where our root locus crosses this imaginary axis, then our locus will be on the RHS, and the moment it is on the RHS, the closed loop system will not be stable because the poles are now on the RHS. Okay, so what we need to check, if we can confirm that locus crosses the imaginary axis, then what it would mean? It would mean that poles, closed loop poles, will be on the RHS because it is starting from LHS, and if it is crossing the imaginary axis, it will be going to RHS, and that would make our closed loop system unstable. Okay, so what we need to check? We need to check whether our locus is crossing the imaginary axis or not. And the moment it crosses the imaginary axis, what will be the real part of the pole? The real part will be 0. We have only imaginary because we are hitting the imaginary axis, right? On the imaginary axis, the real part is 0. So what we need to check, if we write the characteristic equation, which is 1 plus k dash g of s equals to 0, we need to put s equals to j omega, and if we are getting some value of omega and k satisfying our condition that k should be less than 0, or if here it is k dash, so k dash will be greater than 0, then what we can say? We say that the root locus will cross the imaginary axis. Okay, so let's check this condition. So we have 1 plus k dash into g of s equals to 0, and s we have to put as j omega, real part as 0. If we do so, we will be having k dash divided by s cube plus 2s square plus 5s equals to 0. If we put s equals to j omega, what it will be? It will be minus omega cube and minus 2 omega square, be j also, and plus 5j omega equals to 0. So minus omega cube j minus 2 omega square plus 5 omega j plus k dash equals to 0. We can club the real and imaginary parts. So the real parts are minus 2 omega square plus k dash. The imaginary parts are minus omega cube plus 5 omega equals to 0. So individually we have to equate the real and imaginary part as 0, because on the right hand side we have 0. So if real part is 0, then k dash will be equal to 2 omega square when real part is 0. And when imaginary part is 0, then we have 5 omega minus omega cube will be 0. In this case we'll be getting omega equals to 0, and what will be the other values? Omega equals to what will be the other values of omega from here? So omega square equals to 5, so omega will be plus minus of root 5. Okay, so if you put omega equals to 0, then your k dash will be 0. Okay, so k dash cannot be 0 because k dash is 0 at the open loop pole. Okay, so this condition we cannot take. This will not be the correct choice of omega, so the choice will be left with omega equals to plus minus of root 5. So what does it mean? It means that our locus will hit the imaginary axis at j omega, which is plus root 5 j omega, and since it is symmetric, it will hit also the negative, that is minus 5 j omega, plus root 5j and minus root 5j. So that confirms that our root locus is going to cross the imaginary axis, because we are able to find a point on the imaginary axis where our root locus will be present, and that point is plus root 5j and minus root 5j. So that means our root locus is going to cross this imaginary axis, and it cross in the way that it will go to the RHS. So this confirms that if we vary k beyond some finite value, then all our closed loop poles will not be on the LHS, some of them will be on the RHS. Okay, then what can we conclude from here? We can conclude that the closed loop system will not be stable for all k. Okay, for some values of k, if we decrease k to some more values, and if we move towards minus infinity, k minus infinity, then our closed loop pole, two of our closed loop poles will be on the RHS and one could be on the LHS. Okay, so all our poles will not be on the LHS, so the system will not be stable. So what will be the only correct option in this case?
Second option.
Second option, correct. So all are you able to follow this thing? If you have any doubt, you can ask. Okay. Okay, in this question, we have the open loop transfer function of a positive feedback closed loop system. We have a positive feedback, okay, where k is a non-negative real valued parameter. That means k is greater than equal to 0. Okay. Consider the corresponding locus of closed loop poles. Which one of the following statement is true? So we have to find out the region on the real axis which will be lying on the root locus. Okay. Very easy. And we have to follow the concept of complementary root locus because we have k is positive but feedback is positive. It is not negative feedback. So our root locus will be complementary one. Now first let's calculate the closed loop poles. What are the poles? It will be at 4s plus 3 equals to 0. So I think s will be,
-1 and -3.
yes, -1 and -3, correct. And what, sorry, I have written it close, it is open loop poles. And what are the open loop zeros? We have only one zero which is at s equals to 2. Okay, now let's plot this on the s plane. Okay, so we have points at, the poles are at -1 and -3, and the 0 is at s equals to 2. This is the 0. So we have to identify the regions. Okay, let's start from this region, this part of real axis. If we choose any point here, and we look on the right, how many open loop poles and zeros we have?
3.
3, which is odd. Okay, but what we have to check? Even, it should be having even number of poles and zeros because we are having positive feedback with k positive, that is the complementary root locus. So this part will be lying on the root locus or not? This real part? No, because we have odd number of open loop poles and zeros. So this is not going to lie on the root locus. So let's now check this section. So we have checked this section. Now let's check this section. -1 to -3. Pick a point here and check on the right. We have even number of poles and zeros, that is -1 and 2. So we have 2 open loop poles and zeros which is even. So this part will be on the root locus or not?
Yes, ma'am.
Yes, it will be on the locus. Now similarly check this region, -1 to 2.
No.
No, because we have, if we choose a point here and look on the right, we have odd, that is one number of poles. So this is also not the part of the root locus. And what about this region?
Yes.
Yes, because we have a 0 number of poles and zeros, so which is not odd, so it will be the part of root locus. So this is the part of root locus and this is the part of root locus. Now tell me which option is correct. minus infinity to minus 3. Minus infinity to minus 3, no. So minus infinity to minus 3 means this region. So this region is not the part of root locus. Minus infinity to minus 1. No, because minus infinity to minus 1 will include this region as well, which is not the part of root locus. The region minus 3 to minus 1, yes, this part is on the root locus. And the region minus 1 to 2, no, this is not the part of root locus. So the correct option is third one. Okay. So first you have to carefully check what type of feedback is there and what is the sign or range of k. Okay, and then you have to set choose which set of condition you are going to use. So in the lecture that is uploaded in your course, their professor has developed set 1 and set 2, right? So set 1 means the original one, that is with negative feedback and k greater than 0, and the set 2 is of the type positive feedback and k greater than 0. And then you can also cross these terms, and this will give you positive feedback with k less than 0 and negative feedback with k less than 0. Okay, so these two sets, so there you have to follow the conventional root locus design, and there you have to follow the complementary one. Okay, that's how you have to follow. Okay, so for the previous problem, comment on the asymptotes. So you had your transfer function as, let me write it. So your g of s was k into s minus 2 divided by what it is, s square plus 4s plus 3. How many asymptotes will be having?
One, ma'am.
One only, because n is 2 and m is 1, so asymptotes is nothing but n minus m, which is 1. The first option is not correct because it is saying it would have 2 asymptotes. What about other one? It would not have any asymptotes. This is also not correct because at least we have one asymptote. It would have the negative real axis as the only asymptote, and it would have the positive real axis as the only asymptote. Okay, which one is correct? We are following the complementary root locus, so in that case what will be the angle of asymptote? Angle of asymptote, so in the original case it is odd multiple of 180 degree plus minus 180 degree divided by n minus m. In this case we have multiple of 360 degree divided by n minus m. Okay, and k is from 0 to 1, 2, 3. Now since we'll have only one asymptote, so k will be 0, that means 360 degree, or we can say 0 degree. Okay, so 0 degree means negative real axis, positive real axis. What can we say? For that, let's check the point of intersection. Okay, What is the point of intersection? Sum of the poles, open loop poles, minus sum of the open loop zeros divided by n minus 1. So in this case we are having minus 3 minus 1 and zeros are minus 2 divided 1. So it is that is minus 2. Okay, so in our root locus it is going to meet at minus 2. So minus 2 will be this. Okay. Okay, negative real axis, positive real axis, how they are differentiating between these two. We will see this in the next session. I'm not sure how this minus 2 thing will get into the real axis thing. I think it will be a real axis because we have a 0 here and the point of intersection is at minus 2. So anyhow we have this axis here. Okay, we'll see this problem in the next session. Either of these 2 points is correct, but which one we will discuss in the next class. Okay, so let's move on the next question. What will be the breaking point? How can we calculate the breaking point here? Again we have to solve the characteristic equation, differentiate it, calculate for s, and then check if we are getting a positive k or not, because in this problem are we dealing with positive k? Yes, but the feedback is positive. Okay, please try this problem. We have our k into as by bs given as s minus 2 divided by s square plus 4s plus 3. So your a is s minus 2 and your b is s square plus 4s plus 3. Okay, calculate b dash a minus a dash b equals to 0, find s, and then check. So since we have positive feedback, what will be the characteristic equation? It will be 1 minus or plus 1 minus k a by b or 1 plus k a by b. It will be 1 minus k a by b because we are having positive feedback. Okay, the characteristic equation will be this. So k will be nothing but b by a. Okay, and this, for this calculated s should be positive. Okay, so first find out s. So you can see here, earlier we have, when we were dealing with negative feedback, so this condition was k was equal to minus b by a, but now here we have k equals to b by a because we have positive feedback. So these little things you have to carefully observe. So what is b dash? It is 2s. B dash equals to 2s plus 4. And what is a dash? A dash is 1. Okay, now substitute here. It is 2s plus 4 into s minus 2 and 1 into s square plus 4s plus 3 equals to 0. So it is 2s square minus s square is s square, and what final equation you will get will be s square, 4s from here, 4s from here, it will cancel out, so minus 4s, and then minus 11. Okay, then solve for s. So when you solve, you will get s equals to 5.87 and another s will be equal to minus 1.87. Okay, you have to put this k over here, right, which is k equals to b by a, which is equal to s square plus 4s plus 3. So this gives you 2 points on the root locus. So s is 5.87 and s equals to minus 1.87. You are getting 2 points on the real axis, and these two could be, any one of them could be the break in or break away, or it could be nothing. Okay, so first let's check whether we are getting positive k or not for both of these s, and it was s minus 2. Now when you put s equals to 5.87 here, you will get, when you put it, you will get 15.74. k equals to 15.74, which is greater than 0. So this is a valid point on the root locus. And what will be the other point? Calculate k, s square plus 4s plus 3 divided by s minus 2 for s equals to minus 1.87. What k you will get? Please calculate. Any one of you calculated the value of k for s equals to minus 1.87?
0.254.
0.254, which is also positive one, right? So this point also lies on the root locus. Now the question is, which one is break in point? We have to calculate break in point. Which one of these 2 points is a break in point? So the break in point lies between open loop zeros or open loop poles.
Open loop zeros.
Yes. So if we see our point on the S plane, okay, so our poles were at -1 and -3. Let's visualize this thing. And our pole was at s equals to, sorry, 0 was at s equals to 2. Okay. And the points on the S plane we are getting as 5.87, which is somewhere here. Okay. And the other point is at s equals to -1.87, which is somewhere here. Okay. Now can you comment which of these two red points is a break-in point? What about -1.87? Can it be a break-in point? So our root locus is going to start from the open loop poles, that is from -1 and -3, and it will break from here. Okay, because we are starting from somewhere, then we are going to break from this point. Okay, and then we will proceed in such a way that again we will terminate on the open loop 0. So our locus is going to end on the open loop 0. So we are going to come over here again at this 5.87. S equals to 5.87. So which one is the break-in or which one is the breakaway point?
-1.87 breakaway, 5.87 break-in.
Yes, so the correct option is 5.87. Okay. Okay. Similarly, the value of k at the break-in point is, we have already calculated. What was the value of k at s equals to 5.87? It was 15.74. We have already calculated. So option 1 is the correct answer. Are you able to catch this one? Because we have already calculated k, right? Using this condition. Okay. Now similarly, as we have already calculated, what is the breakaway point? It was s equals to -1.87. And then what was the value of k at that point? It was 0.254. Okay. Now, okay. For this problem, what are the crossover points? Crossover points means, as we have already seen in this root locus, that is not the exact one. We have drawn it by intuition only. But we can say that it starts from the open loop pole, and at the breakaway point it is going to diverge, and then finally it has to converge to the open loop 0. Then it must cross the imaginary axis. it must cross the imaginary axis. So at what point it will cross the imaginary axis, that we need to calculate. Okay, so how to calculate that one? Just put s equals to j omega in the characteristic equation and solve for k and s. So the characteristic equation is 1 minus k into g, because we have positive feedback here. So try to calculate it. Let me share my screen. Okay, so we need to solve 1 plus even minus, because we have positive feedback. 1 minus k into gs equals to 0, and g was s minus 2, s plus 1, s plus 3. S minus 2 divided by s plus 1, s plus 3 equals to 0. We have to put s equals to j omega. Then it will be j omega minus 2, j omega plus 1, j omega plus 3 equals to 0. So it will be, let's multiply directly. It will be minus omega square and j omega 4j omega plus 3 minus kj omega and plus 2k equals to 0, right? Let's keep the real and original points separately. So minus omega square plus 3 plus 2k, right? And the imaginary one we have plus 4j omega minus kj omega equals to 0. So both the real and imaginary parts should be equal to 0 to match the RHS. This would give us, first if we put the imaginary part as 0, it would give us 4 omega equals to k omega. So our k equals to 4. We have calculated k equals to 4 at the crossover point. That is, when k equals to 4, our root locus will cross the imaginary axis. At what point it will cross, that we can get by putting this real part equals to 0 and putting k equals to 4, and then by calculating this equation we will get the omega. So from here k will be equal to 4. Clear to everyone?
Yes, ma'am.
Okay. Yes, and then the closed loop system for this problem will be stable for what range of k? How to check that? That's very interesting because we have already seen that this was our open loop 0 at 2. This was our open loop poles -1 and -3, and we have already seen that we are going to break from here at around -1.87. Okay, and then at some 5 point something value we are going to cross the imaginary axis and then come again at this point, and we will converge at 2. Okay, so what was the, so here the value of k is 0 because we are starting from open loop pole, and here the value of k will be infinity because we have open loop 0 here. Now what was the value at this point when we hit the imaginary axis? What was the value of k? It was k equals to 4. We have already calculated in the previous question. Now we started from k equals to 0, so our locus was all on the left hand side. We were increasing k up to k equals to 4, and up to that point we were still on the LHS. That means our closed loop poles are strictly on the negative half of S plane, and then the moment we have k equals to 4 and then we increase k, our closed loop poles were on the RHS, right? So the closed loop system in this case is stable for what range of k? Now can you identify with this story?
K less than K less than 4.
Yes, because for k less than 4 we were explicitly on the left half. All the closed loop poles were on the left half of plane. So the correct option is k less than 4. Okay.
Ma'am, please repeat how you calculate k value is equal to 4 on the imaginary axis.
Okay, so what we have done in the previous question, we calculated the point the root locus will hit the imaginary axis. So what does it mean? It means that there exists a point on the root locus such that the roots are purely imaginary. Okay, that is the only case when we are going to hit the imaginary axis, because the root locus is nothing but the locus of closed loop poles. So the moment the closed loop poles are purely imaginary, that means we are explicitly on the imaginary axis. So what we have done, we have find out the characteristic equation, which is 1 minus k into gs for the case of positive feedback. Okay, and then we put s equals to j omega only, because we want to check if there is explicitly imaginary poles, closed loop poles are there or not in the system. Okay, so we put s equals to j omega and we solve the characteristic equation, and then we get finally this relation. Okay,
Clear, ma'am.
clear? Okay, now in this question we have a unity negative feedback system with k greater than equal to 0, and the root locus of the system is shown on the right. Identify for what value of k the system will have a pole at -1 plus j. Okay, so there is some open loop transfer function g of s with k positive, and we have a negative feedback, and for this system the root locus is drawn on the right. That is the root locus is this part, that is this part, and this circle. Okay, so for this we have these 2 points are the open loop zeros and these 2 points are the open loop poles. Okay, so this is -1, -2, -3, -4, and this is minus j point, this is 0, and this is plus j. You can answer this question within a fraction of a second if you are able to see the root locus carefully. You need not to calculate anything. You just have to find the value of k such that the system will have a pole at -1 plus j, closed loop pole at -1 plus j. Now first, where will this point lie on this S-plane? -1 plus j1. So -1 is this point and plus j. So they are talking
Left
about
half.
this point. -1 plus j. Okay. This point in blue. Now tell me whether this point is part of root locus or not.
No.
No, because the root locus is already drawn and this point is lying away from the root locus. So are we able to, so as this is not the part of root locus, what does it mean? This point is never going to be the pole of the closed loop system. So will there exist any case such that this could be the pole of closed loop system? So what is the definition of root locus? Root locus, what we are drawing here? We are drawing the closed loop poles by varying the open loop gain k, right? So it
From
is the trajectory of the closed loop poles. It is nothing but the trajectory of closed loop poles with respect to k. Okay, and the question is asking, if we are varying k, then is it possible that for some value of k, this -1 plus j point will be the pole of this closed loop system? So the answer lies in the definition only. The root locus is already drawn, which is the locus of the closed loop poles with respect to gain k. Okay, and since this point is not the part of root locus, what does it mean? There will be no k such that this point will be the part of the root locus, because for all values of k the locus is already drawn. Okay, so what will be the answer?
For no positive value of k.
Yes, for no positive value of k, this is going to be the pole of closed loop system. Clear to everyone? Okay, so this question I've already solved in the previous session. You can watch on the YouTube also. Okay. Okay, you can note this point, this question, and we can discuss it in the next session. So in the question we have open loop poles of a third order unity feedback system which are at 0, -1 and -2, and we are considering the frequency corresponding to the point where the root locus of system transits to unstable region, and let that frequency be equal to k. Okay, that omega equals to k. Now suppose we introduce a 0 at -3 in open loop transfer function, then we have to comment on which of the following statements is true. Okay, so we'll discuss this problem in the next session. If you have any doubt, we can discuss or you can ask. And the other question that we have left about the asymptote, that also we will see in the next session. So these we will start our next session with these two questions only, and then we will discuss further questions. Apart from this, if anyone having any doubt, you can ask. Okay, then we'll meet next week from 6 to 8, and we will solve some more problems on root locus and maybe Bode plot also. Okay, then let's meet next week. Goodbye.
Thank you, ma'am.
Thank you.